where we stopped yesterday. So what is the process involved, by the way? We all know filtering is nothing but convolution, and convolution in the time domain was equivalent to multiplication in the frequency domain, right? The way we studied it in signal processing. Similarly, here the convolution in the yeah okay. So similarly here, what's going to happen? The convolution in the spatial domain, right? We did. You remember, right? You have done the assignments which I asked you. What you would do there, by the way, you will have a filter function, right? What we call the mask, and these two we will simply convolve this convolution, correlation, whatever you call it. As and when the mask is symmetric, it doesn't matter, right? That's what we did in spatial filtering. Okay. That's what we did in filtering. Now the same convolution or correlation, whatever it is, it turns out into a multiplication here in the spatial frequency domain. Okay. But the catch is we need to do some sort of pre-processing. We need to do some sort of pre-processing. This part anyway is known, right? You have to take the transform, multiply it with the Fourier transform of the mask. So what is this HU comma V? This is nothing but the Fourier transform of the mask. Okay. This is nothing but the Fourier transform, whatever the mask you had created earlier. So in this particular chapter, we will be discussing about the masks in the frequency domain only. Okay, because they are easier for us to design. Okay. So let us see the purpose now. So what it is, basically it is multiplication. Let us see what is the detailed process, what does it involve, and what is the reason for it. Okay. So what is it all about? So basically there are different band pass, low pass, high pass, and band reject filters available for us depending on the scenario. So generally there is low pass and then there are high pass filters. Low pass filters basically give you the average intensity region. Okay, whereas the high pass filters, they uh, you know signify the edges, right? So if at all I have a Fourier transform, I have the Fourier transform, say the values in the center indicate the low frequencies and the values in the corner indicate the high frequencies. So low pass filtering is all about picking up the frequencies in the center. Okay. Whereas high pass filtering is all about picking the frequencies in the corner. Okay. What we call the details, whatever we call it as the details. Okay. We call them as details. Okay. So that's it. So here they have given a diagram. So as you can see, the edges you can see have been enhanced. The edges have been enhanced here because sudden change or the edge is nothing but high frequency and all the minute details here, minute details. Whereas this particular bar here almost looks as if it were a of single intensity, but these kind of these dents or bumps have been picked up by the high pass filter, whereas they have almost vanished in the low pass filter. Okay, somebody may be interested in the bigger picture, whereas somebody may be interested in the finer details. Depends on the requirements of the developer. Okay. Depends on the requirements of the developer. Okay. So okay, so now what do we do, by the way? The pre-processing that I spoke about earlier, multiply the input image by -1 to the power x plus y. So what is this thing, by the way? So let us try to understand what is this. So why do we need to do multiply? What author is telling is, if at all you want to process a image using frequency domain, if at all you want to filter, okay, what you have to do? Filter using frequency domain. So this h of u comma is the DFT of the mask, mask in the frequency domain. F of u comma v, f of u comma is our input image, the frequency domain, the DFT of the input image. What author is telling is this particular image shall be pre-processed such that we multiply it by -1 to the power x plus y. Now why do we need to do that? Why do we need to do that? For that we need to again go back to the topic that we were discussing yesterday, right? Why we need to do that? Actually, that value is derived from this particular function. Wait a second, let me uh, yeah, one second. Okay. So now what are you seeing, by the way? You are seeing the screen. So this is the copy of the textbook. Can you see the screen? Somebody please ping. Can you see the screen? Hmm? Okay. Can you? Somebody please message. Can you listen to me? Can you see the? Okay. Okay. Hmm? So here you see, here there is a thing. Okay. So why do we need to do this multiplication by minus one? Actually, what we are trying to do, actually, what we are trying to do is, we are trying to, I was telling you yesterday about the way this FFT shift function works. Okay. FFT shift function, what does it do is, if at all you have a DFT signal, something like this, we have seen, right, how a typical DFT looked like in MATLAB. So it would have some, say, from 0 to n minus 1, the values in the first half and the second half. So FFT shift function, if at all you do, what it does, it moves this part on the left side, so that you get an image something like this. Okay, same in the textbook style, a textbook style DTFT sort of image for DFT. Similarly, same is the case with images also. If at all you take a DFT of a two-dimensional image, actually, if at all you're talking about DTFT of a two-dimensional image, the value, the DC, should have come at the center. But it so happens that all the DC will be now actually accumulated in the corner. Okay, the DC will be accumulated in the corner, and all the high frequencies will be accumulated in the center. So as I told you, the entire DFT in one dimension can be broken into two parts. So similarly, a two-dimensional DFT can be broken into four parts. Okay, four parts. This is one, say two, 3 and 4. What we have to do, this is better understood. If at all it's kept in this particular manner, it will be a wrong interpretation. We want it to be in this particular format. We want it in this particular format. Whatever I'm drawing on the left side, how do I want it? I want all those four DC intensities in the corner to come at the center. How do I do that? So that my fourth quadrant comes in here, my second quadrant comes in here, my first quadrant is moved here, and my third quadrant is here. Okay, that means this corner shall be moved here, this corner shall be moved, this quadrant shall be moved here, and so on. So the task is let us only concentrate on this particular quadrant. Okay, we know DFT was periodic. Remember, DFT was periodic. That means if at all I have a 4-point DFT, x of 0, x of 1, x of 2, and x of 3, what will be x of 4? DFT is periodic. So a one-dimensional DFT is periodic. So x of 4 will be nothing but x of 1 only. X of 5 will be nothing but x of 2 only. So that if at all I happen to move the value in the first quadrant to the fourth quadrant here, if at all I move this particular thing here, automatically from the previous quadrant, these values will also be moved. Okay, these values also be moved. So to how much distance do I need to move it? This point, the point here shall be moved from here to the center, right? This, the point at origin, shall be moved to center. Suppose I have a 640 into 480 image. Suppose I happen to have a 640 into 480 image. Okay, 640 pixels horizontal, 480 pixels vertical. I need to move it by 640 divided by 2 locations horizontally, 480 divided by 2 locations vertically, downwards. Okay, now this particular number from the DFT point of view results in an expression something like this, where you get an m 2 pi m into m by 2. So m into n by 2 gives you a pi by 2. Okay, pi by 2, which always results in a value of -1, which always results in a value of -1. I hope now you get it. Okay, and we know what is that property? Multiplication by an exponential in the time domain is shift in the frequency domain, right? And a shift in the time domain is multiplication by an exponential in the frequency domain. So this is what happened. Hmm? This is what happened. And since the values were chosen as m by 2 and n by 2, because it's the factor by which you wanted to shift our pixels to, the automatically the value turns out to be minus 1. Okay, automatically the value turns out to be minus 1. So the shift in the spatial domain is nothing but multiplication by an exponential in the spatial frequency domain, but that value will always be minus 1. Okay, now I hope you understood the concept behind it. Okay, so if at all you're doing this in MATLAB, you just have to use the ready function fft shift. Okay, it will be done automatically, or you are free to use this thing only. Okay, we will usually do fft shift. Okay, got this? Comfortable? Understood? Somebody please message if at all you have got any vague idea of the thing. hmm? Did you, Sushma, did you get this thing? Abhishek, hmm? We'll come to this. Okay, by the time this class ends, I will go to the topic. Okay, I will go to the topic and now go to MATLAB, and I will show one example also. Okay, so what does the pre-processing involve? So now we know why minus 1 to the power x plus y. It is to bring the values from the corner to the center. Okay, just the way DTFT looks like. Okay, because that's the way we have usually analyzed all filters for. Then afterward compute DFT. Then afterwards multiply it with the frequency transform of the filter. Okay, if it is a spatial filter, so usually we are not talking about impulse response. Now, you might have understood even in DSP with it, the frequency responses are what we are comfortable with. That's what we'll be doing. Get the results. Finally, once you get the results, you have to do the reverse operation of multiplying by minus 1 to the power x plus y once again. Okay, there you get it. Okay, there you get the thing. So what sort of filters, by the way, do we have? What sort of filters do we have, by the way? So can you see the screen, by the way, filtering in the domain? Wait a second. Full. Okay. So what sort of filters do we have? Let us see. Yes. Hmm. So, hmm. So filters can be smoothing filters, a low pass filter, okay, or the filters can be sharpening filters. Now let us understand what is meant by a sharpening filter. Sharpening filters are those filters which will only pick the edges, the change in the intensities. They will pick the edges. Okay, let us see. Usually the method we do is always the color images are converted to grayscale, and they are processed. Okay, why bother about 3 dimensions? So usually not bother about, it will be too complicated. Okay, so here, for a grayscale image. Okay, so here you can see when you apply the high pass filter, all these edges whatever I had stressed earlier, okay, they have been picked. Okay, earlier we discussed about this Laplacian, right? Laplacian, they also picked that. Anyway, we'll connect all the dots there. So that's a high pass filter. Okay, that's the high pass filter. What else do we have got? Okay, so this is what author was telling. So as I told you yesterday, data types are something that we should be careful about. Okay. So low pass filters, they average out the thing. High pass filter, they stress on the details. Voice breaking. Okay, sorry. Hmm. Okay, now wait a second. Wait a second. Now can you listen to me? Now how is it? Okay. So yeah, that's now can you listen to me? Can you? Somebody please message. Yeah. Sorry for that. Now can you? Hmm. So the internet connection is sort of poor, from last 2 days. So it's our mobile internet. Okay. Hmm. Okay, so yeah, now let us quickly see a typical filter. Okay, let us quickly see a typical low pass filter. Okay, so an ideal low pass filter. What was the story that we used to tell you in our digital signal processing or in your analog processing? Filters cannot be ideal, right? We always told that filters cannot be ideal. Ideal filters are only stories, and we have to go for some sort of slope, something like this. Larger the cutoff, more is the order. Here in the frequency domain, if at all we are talking about images, nothing like that. Okay. In images, say this is the frequency domain of a mask. Okay. Suppose this is the Fourier transform of a filter mask, and let me tell you, at center point is all the DC and low frequencies. So this is the low frequencies. As and when we move to the corner, then we will have high frequency. As and when we go to the corner, we will have high frequency. So if at all the author, okay, if at all the author tells you that there is all ones here, okay, uh, white is nothing but a one, right? Suppose there is all one here and all zeros here in the corner. Are you convinced that this particular filter mask, if at all I multiply this mask with the Fourier transform of the image, say I multiply this mask with the Fourier transform of the image, what will happen? If at all I multiply this mask with the Fourier transform of my image, all these frequencies, all the frequency components where there is black means zero, it is simply gets multiplied by zero, and all these higher frequencies get vanished, and you will be left with only the frequencies till a particular radius. You will have frequencies only till a particular radius. Convincing enough? Okay. Do we call that as a low pass filter? So can we call that as a low pass filter? Somebody please. Okay, so what is the idea? You have a circle, and I intend to multiply this with the Fourier transform of the my image. Okay, and all these values, whatever you see as black, they are all zeros. So when I multiply this particular mask with the image, bit pixel by pixel, okay, this is a not a matrix multiplier, this is a scalar multiplication, pixel by pixel. What's going to happen? Automatically all the values above a certain radius will be automatically going to zero, and we end up picking only the low frequencies. So is that fine for you? So that is our filter. By the way, what sort of filter? It's an ideal filter. You can see it's a ideal filter. Below the radius, okay, from center 10 pixels all the sides. Okay, pick all 10 pixels on all the sides from the center point. That's what this means. We'll call this d naught as the radius, and that will be our low pass filter. That will be a low pass filter. Okay, that will be our low pass filter. Now suppose I have a mask something like this, and then I have a circle something like this. For a change, I will have black in the center up to certain radius, and on corners, if at all, I have white. Okay, are you getting? In the center I will have black, and in the corner I say I have white. So what sort of filter it will be? In the center it was white, and in the corners it was black. The filter was a low pass filter. Now for a change, say in the center say I have black, and in the corners, okay, so here and all say I have white pixels. Then what sort of filter it will be? Somebody please tell me what sort of filter it will be. White in the corners, black circle in the center. What sort of filter do you think it will be? Somebody message. I will let you unmute yourself also if at all you want to answer. Are you? Can you listen to me? Are you there? That's what I thought. Hmm? Are you there? Everybody just type a hi or attendance. Will do that now. Okay, you are there, right, Sushma? Why you are not answering? Hmm. I'm asking a question here. That's why I asked the attendance. Okay. Yeah. Said hi for attendance also. Please answer me this thing. Hmm, Please answer me this thing. Somebody please tell me. Hmm? Yeah, yeah. Hi. Fine. Quickly, me let answer this. Say I have instead of a white. Say I have black circle and corners white. Yes, Ranjana. It is going to be a high pass filter. Then it's going to be a high pass filter. Okay. So similarly, say I have say I have a circle, something like this. Inside this also I have a circle. Okay. Inside this I also have a circle. And inside that circle also I have all black. Say all black. I have a transform mask such that I have a circle outside. I have black above certain radius. Below certain radius also I have black. In between I have a ring. Now what does that mean? What sort of filter would that be? What sort of filter would that be? It's going to be a band pass filter. It's going to be a band pass filter. Above certain, say this particular radius from center is say a D1, and the outer radius, say for this radius is say D2. Wherever there is white, a 1, the values will be forward as they are. Wherever there is black, the values are suppressed. Okay, cool. Similarly, if at all we are talking about a band stop filter, then what's going to happen? Here we'll have white, inside also we'll have white, in between the circle that will be black. Okay. I hope you got that particular thing. Okay. So how do we describe it, by the way? Up to certain radius, say 10 pixels, 20 pixels, 30 pixels, or 50 pixels. If at all you get by the formula calculation 9.5, 9.6, round it to the next pixel and so and so. And then you get the values. Okay, there you get the values. That is how we describe the filters. Okay, and why do we have to do this particular thing? Because the center is not the actual number starts on 0. Okay, we have to go to the center. From there we have to pick the corner. That is why u minus m by 2, v minus n by 2. Okay, from this particular point we have to come to center. From there we have to pick the values. Okay, that is the meaning of this particular d. That is the meaning of this particular d. Okay, so what sort of impact, by the way, what sort of impact it's going to have? So as you can see here, you see so there is this particular image author has shown. Okay, the filter can have several radius. See here, there is one circle. Okay, this is of smaller radius, maybe 5. Then one more circle of little larger radius, say maybe 15, then 30, then 80, and so and so. Okay. Larger the circle, more details will be picked up, or more average values will be picked up. And what will be their impact, by the way? What will be their impact? So here you can see this is the original image. Then there are the various filters. These are not the masks, by the way. These are just the indicated radii. Okay. The radius have been indicated here by the author. And this one here, this, by the way, is nothing but the 230. This is 230. Okay. So you can see, and how the things going to be original image. Okay, so if at all you tend to Hmm. if at all you tend to take the smallest radius, only lowest details are picked. Maybe you increase the radius, more details are picked. Increase the radius, more. Okay. So finally, for the largest radius, okay, 230, 240, you will get the image as it is. This is the average value you can see in this particular pixel, maybe. Okay, depending on the side, it has simply picked up the average intensity value, some black patches here. And then when you increase the size of the image, then you are getting more details. Okay, so larger value gives you more details. That's the low pass filter. Anything peculiar, by the way, do you observe in this particular image? Anything peculiar do you observe in this particular image? Somebody, are you there? Anything peculiar you observe in this particular images? In these particular images, anything peculiar you observe here? Hmm. Can you observe there is an aura there, right? Usually you can see here above this particular A, there is a border, right? A sort of etching and embossing sort of thing. You can see. Do you observe it? Do you observe it? There is a aura sort of thing, aura sort of thing. Can you observe it? Somebody please message. Somebody please. Can you observe this particular Sushma? Can you observe this thing? Ranjana, Abhishek, can you observe this? Some sort of an aura, some sort of an aura around the image. Okay, a ring. Okay, the name they have given is ringing effect. Okay, the name they have given is the ringing effect. Okay, okay, we'll also observe this. So this has got something to do with the Gibbs phenomenon. Remember, in DSP we studied this rectangular window. Why rectangular window is bad? Because the sudden transition in the rectangular window would cause the peak overshoots and the undershoots. Remember, that was the issue with the rectangular window, the Gibbs phenomenon. Okay, this is we can see it here literally. Now let me take you to MATLAB. Let me take you to MATLAB. Be there, and I will show you one filtering thing. Just be there. I will conclude this in this 10 minutes only, 8 minutes only. Okay, now can you see my MATLAB screen? 7 more minutes remaining. Okay, hopefully I will finish in that. Hopefully. Can you see my MATLAB screen by the way? Somebody please message. Okay, so here I have picked up. Okay, thank you. So here what I have done is I usually how to get the images by the way, simply go to paint. Okay, what you have to do is you should just go to paint. Type in paint, go to paint. Hmm, Let me do that. Let me do that. Okay, so here I have taken a image from I have created a mask from just paint only. Okay, I have created a mask from paint. Okay, so how does this mask look like? Let me show you the mask. So here, let me run this thing. Mm. Yes, I was telling you. Now can you see my paint? Can you see my paint thing? I was telling you how to create a mask. So creating mask is easy. First you have to, can you see my paint editor? Can you? Okay, so creating mask is nothing but you should go and take the image size. The template should match. Okay, your horizontal and vertical pixels, they should match exactly that of your image which you want to manipulate. Okay, matrix size matching is very important. Then you decide what sort of filter you want, and this particular circle what you take, it too should be there in the center. That too should be there located exactly in the center. And then I will take this paint bucket and then I will fill outside. Now you can see this particular thing what I have done now is my low pass filter. Okay, this is my low pass filter. If at all you want that of a larger radius, maybe you can do that also. So you want a high pass filter, you can do high pass filters also. So how do you do a high pass filter by the way? Oh god, wait a second, wait a second. Hmm. So wait a second. So select a mask of your size, then fill inside of the mask with the Okay, inside is black, then outside, inside is should be black. Okay, wait a second. Okay, this is black, and the outside it should be. Wait a second. Wait a second. Okay. So this particular image, can you see this particular thing? This will be nothing but this is a mask of our high pass filter. Only thing you have to be careful about is the diameter size. How much more you want? Larger the size, more will be the bandwidth. Okay. Something like that. So that will be easy. Okay. Now let us go to our MATLAB thing. Hmm? Let us go to MATLAB. Okay, so the mask which I have chosen in the MATLAB has now popped up. So this is the mask that I have chosen in the MATLAB. I have made sure that the number of horizontal and vertical pixels, whatever I have, they exactly match that of the image that I want to manipulate, and the center point also. I have made sure that also matches. And yeah, there are some mistakes. Fine. Okay, homemade mask. Okay. Okay. So there it is. Now let us see what sort of manipulations we want to do. How does this mask typical look like? Okay. Whenever you create something in Paint, it will be usually a grayscale. So you have to convert it from RGB to, it will be color BMP. You should convert it from RGB to grayscale. Okay. RGB to grayscale. And let me show you how the yeah, are you there? I will start a new session. Okay. Start a new session. Wait a second.